Welcome to this problem walkthrough. Today, we'll explore problem number 1236, titled Web Crawler. We'll discuss the problem's requirements, examine potential solutions, and work through the steps to tackle it efficiently. Let's dive in. In this problem, you are tasked with implementing a web crawler. The starting point for the crawler is a URL, called Start URL. Your goal is to visit all the links that belong to the same hostname as the Start URL. A web page's HTML often contains multiple hyperlinks, and these links can lead to other pages. To help with this, you'll use an interface called HTML parser. This interface has a method called getURLs that takes a URL as input and returns a list of all the URLs that are accessible from that page. The solution you write will be a function called crawl, which takes the starting URL and an HTML parser object as input and returns a list of all the URLs that match the criteria. The inputs to the problem are as follows: start URL, which is a valid URL in the format http://hostname/path/ and HTML parser, which is an object of the HTML parser class. The output will be a list of all URLs that share the same hostname as start URL. These URLs can be returned in any order. The hostname, in this case, is the part of the URL between http:// and the first //. For example, in the URL http://example.com/test, the hostname is example.com. Your crawler should only visit URLs with this hostname and ignore others. Additionally, no URL should be visited more than once to ensure efficiency. You can safely assume that all URLs are valid and there are no edge cases like infinite redirects to handle. To help clarify, let's look at an example. If the start URL is http://news.yahoo.com/news and the HTML parser.getURLs method for this page returns 4 links: http://news.yahoo.com/news, http://news.yahoo.com/news/topics, http://sports.yahoo.com, and http://yahoo.com. The output should include only the URLs http://news.yahoo.com/news and http://news.yahoo.com/news/topics. This is because the hostname of start URL is news.yahoo.com, and only URLs that match this hostname are valid. Links like http://sports.yahoo.com and http://yahoo.com are ignored as they belong to different hostnames. The output is simply the list of URLs that share the same hostname as start URL. Now, let's consider a second example. If the start URL is http://example.org/a and the HTML parser.getURLs method for the page returns links to http://example.org/b and http://example.org/c, the crawler would follow those links. When it visits http://example.org/b, it discovers a link to http://example.org/d. Visiting http://example.org/c and http://example.org/d reveals no new links. The result is a list containing all the unique URLs with the hostname example.org, which are http://example.org/a, http://example.org/b, http://example.org/c, and http://example.org/d. The crawler systematically visits pages, collects links with the same hostname, and ensures no URL is visited more than once. Finally, there are a few important constraints to keep in mind. The number of unique URLs reachable from start URL will range between 1 and 10,000. The length of any URL will not exceed 300 characters, and all URLs provided are valid. The getURLs method will never return duplicate URLs for a single page, and the crawler may start with URLs that include query parameters or fragments, such as http://example.com/page, query equals 1 or http://example.com/page hashtag section. These should still be treated as part of the same hostname. Importantly, your solution must avoid visiting the same URL more than once to prevent infinite loops and redundant work, ensuring the crawler operates efficiently. To solve the web crawler problem, we can start by considering a brute force approach using either depth-first search (DFS) or breadth first search, BFS. The key idea here is that the web can be represented as a graph where web pages are nodes and hyperlinks are edges. Starting from the start URL, the goal is to crawl all URLs that belong to the same hostname, which means we need to restrict our traversal to only those links that share the same domain as the start URL. To achieve this, we first extract the hostname of the start URL. Then, by using the HTML parser interface provided, we can fetch all the links on a given page. For each link, we check if its hostname matches the one we extracted from the start URL. If it does, we recursively or iteratively crawl it, ensuring we don't revisit URLs by maintaining a visited set. While this approach is straightforward and guarantees that all reachable URLs within the same hostname are visited, it can involve redundant processing if the visited set is not managed carefully. The time complexity of this approach is O, V plus E, where V is the number of unique URLs and E is the number of hyperlinks, while the space complexity is O, V, due to the visited set and the recursion stack in DFS. Now, to make the solution more efficient, we can optimize the brute force approach using a BFS strategy. BFS is particularly advantageous because it explores URLs level by level, which can be more memory efficient compared to the deep recursion stack of DFS. We can also use libraries like erlib and Python to simplify the parsing of hostnames and ensure that the comparison of hostnames is both accurate and efficient. Additionally, we need to handle edge cases such as malformed URLs or links leading to external hostnames. In this optimized BFS approach, we start by enqueuing the start URL and marking it as visited. Using a queue, we process URLs one at a time. For each URL, we fetch its links using the HTML parser, filter out those that don't belong to the same hostname, and enqueue only the unseen ones. This ensures that every URL is processed exactly once, eliminating redundancy. The time complexity remains O, V plus E, similar to DFS, but the space complexity is also O, V, with memory usage attributed to the visited set in the BFS queue. This optimization makes the solution safer and more scalable, especially for large inputs. When deciding between DFS and BFS, there are trade-offs to consider. While DFS is sometimes simpler to implement, it risks stack overflow for deep or large graphs due to its recursive nature. On the other hand, BFS avoids this risk, as it uses an explicit queue instead of recursion. BFS does require additional memory for the queue, but it is generally easier to debug and safer for large-scale problems. Based on these considerations, we chose BFS with efficient hostname filtering as our final strategy. This approach strikes a balance between simplicity, safety, and performance. It effectively handles edge cases, such as malformed URLs and external hostnames, while ensuring that every URL is processed only once thanks to the visited set. This makes the solution robust and scalable. By exploring URLs layer by layer, BFS also provides better memory management, making it well suited for the problem at hand. To implement this solution, we use Python's deque for the BFS queue and the rlparse library to extract hostnames. The crawl function begins by defining a helper function get_hostname to parse the hostname from a URL. We initialize the hostname of the start URL, a visited set to track processed URLs, and a queue to manage the BFS traversal. Starting with the start URL, we process each URL in the queue by fetching its links using the HTML parser. For each link, we check if it is unvisited and belongs to the same hostname. If both conditions are met, we mark it as visited and add it to the queue. This ensures that all URLs within the same hostname are crawled exactly once. Finally, the function returns the list of all visited URLs. This implementation efficiently combines BFS with hostname filtering, providing a robust solution to the problem. The goal of this problem is to simulate a web crawler that starts from a given URL, start URL, and explores all URLs that can be reached while staying within the same hostname. This means that as we navigate from one page to another, we must ensure that we don't cross over to a different domain. Additionally, we should avoid revisiting URLs we've already seen to optimize our process and avoid infinite loops. The first step in the algorithm is to extract the hostname of the starting URL. For example, if the URL is http://example.com/page1, the hostname is example.com. This helps us identify which URLs are valid for crawling. By limiting the crawl to this hostname, we enforce the problem's constraints and ensure the crawler behaves as expected. Once we've determined the hostname, we need to set up the data structures that will help us manage the crawling process. First, we initialize a queue or a stack to hold the URLs to be processed. The choice between a queue and a stack depends on whether we want to implement breadth-first search, BFS, or depth-first search, DFS. BFS processes URLs level by level, while DFS dives deeper into one path before backtracking. Next, we use a hash set to track visited URLs. This ensures that we don't process the same URL multiple times, preventing cycles and redundant work. With these structures in place, we enqueue the start URL into the queue and mark it as visited. Now we can begin the crawling process. While there are still URLs to process, we dequeue a URL, fetch its HTML content, and extract all links from the page. Each link is validated to ensure it belongs to the same hostname and hasn't been visited yet. Valid, unvisited links are then added to the queue and marked as visited, allowing us to systematically explore the web graph. The crawling process continues until there are no more URLs left in the queue, at which point the algorithm terminates. At this stage, the visited set will contain all unique URLs that are reachable from start URL and belong to the same hostname. There are several key insights to note here. First, matching hostnames is critical to respecting the problem's constraints, and extracting the hostname at the start avoids unnecessary checks later. Second, using a visited set is essential for avoiding cycles and redundant work, ensuring our crawler operates efficiently. When deciding between BFS and DFS, consider your specific needs. BFS is useful for shallow exploration or finding the shortest path, while DFS can be more memory efficient. Finally, edge cases like URLs with different schemes, trailing slashes, or query parameters need to be handled carefully. Normalizing URLs can address these issues and ensure we don't mistakenly treat equivalent URLs as different. Additionally, broken or inaccessible links should be skipped to maintain robustness. The data structures we use are fundamental to the performance and correctness of the web crawler. A queue or stack is used to manage the URLs to be processed. For BFS, a queue ensures URLs are processed in the order they are discovered, while for DFS, a stack allows us to process the most recently seen URL first. Both approaches guarantee systematic exploration of the web graph. A hash set is equally important, as it tracks all visited URLs. With O(1) lookup and insertion time, the hash set prevents revisiting URLs and avoids infinite loops. Additionally, we rely on a parser to extract links from the HTML content of each page. A tool like Beautiful Soup in Python can efficiently parse anchor tags and provide the URLs for validation. By combining these components, we ensure the crawler is both efficient and accurate in adhering to the constraints of the problem. Let's analyze the algorithm's complexity. For time complexity, let n represent the total number of URLs reachable from start URL. Each URL is processed once, and operations like checking the visited set or enqueuing URLs take O(1). However, extracting links from each page depends on the size of the HTML content, which will approximate as m, the average number of links per page. This gives a total time complexity of O(n*m). For space complexity, the visited set requires O(n) space to store all processed URLs. Additionally, the queue may also require O(n) space in the worst case for BFS, though DFS can have a smaller memory footprint depending on the depth of recursion. To optimize the crawler, we can use concurrent requests to fetch multiple pages simultaneously, significantly speeding up the process. Normalizing URLs is another crucial optimization, as it ensures variations like trailing slashes or query parameters don't lead to duplicate entries in the visited set. Finally, robust error handling is essential to gracefully manage broken links and inaccessible pages, ensuring the crawler doesn't fail unexpectedly. Here, we begin implementing the solution for the web crawler problem. First, we import the necessary libraries, deque from the collections module, which will help us manage our queue, and urlparse from urlib.parse, which will allow us to extract the hostname from a URL. The problem provides an HTML parser interface to retrieve URLs from a page, though its implementation is hidden. We then define the solution class and its crawl method, which takes start URL and an HTML parser instance as inputs. To track the URLs we visit, we initialize a set called visited. We also create a queue using deque and add the start URL to it. Next, we extract the hostname from the starting URL using URLparse, which ensures we only consider URLs from the same domain as the starting point. Inside the while loop, we process URLs from the queue, starting by removing one from the left using popleft. If the current URL has already been visited, we skip further processing for it. Otherwise, we add it to the visited set, marking it as processed. After that, we retrieve all URLs on the page by calling html_parser.getURLs for the current URL. For each URL retrieved, we use URLparse again to check if the hostname matches the starting domain. This ensures that the crawler stays within the same website and doesn't venture into external links. If the hostname of a next_URL matches the start_hostname and the URL hasn't been visited yet, we append it to the queue for further processing. The while loop continues until the queue is empty, meaning all reachable URLs within the same domain have been processed. Finally, we return the visited set as a list, containing all the URLs that the crawler visited. This approach ensures that each URL is processed only once, and the crawler respects domain boundaries while systematically exploring all valid links. Here, we begin implementing the web crawler in Java. First, we import the necessary libraries java.util for data structures and java.net for handling URLs. The problem provides an interface called HTML parser with a method getURLs that retrieves all URLs found on a given page. The implementation of this interface is hidden, so we only use it as described. In our solution class, we define the crawl method, which takes a start URL and an instance of HTML parser. We initialize a set called visited to track the URLs we've already processed, ensuring we don't revisit them. Additionally, we use a queue to handle URLs in a breadth-first search manner, starting by offering the start URL to the queue. To ensure we only crawl URLs within the same domain, we extract the hostname from start URL using a helper method called getHostname. Then, we enter a loop that processes URLs in the queue. For each URL, we check if it has already been visited. If it has, we skip to the next iteration. Otherwise, we add it to the visited set and retrieve all URLs linked from the current page using html_parser.getURLs. For each of these linked URLs, we check if its hostname matches the original domain and if it hasn't been visited yet. If both conditions are met, that the URL belongs to the same domain and hasn't been visited, we add it to the queue for further processing. This ensures our crawler remains focused on the same domain and avoids unnecessary reprocessing of URLs. Once all URLs in the queue have been processed, we convert the visited set into a list and return it as the result, which contains all unique URLs within the same domain. Finally, we have the getHostname helper method. This method takes a URL string as input and uses Java's URL class to extract the hostname. If a malformed URL exception occurs, indicating that the URL is invalid, we handle it gracefully by returning an empty string. This approach ensures robustness in cases where parsing the URL fails. With these components, the implementation completes a breadth-first search, effectively crawling all valid URLs within the specified domain. In this example, we are tasked with crawling a simple domain starting at http://example.com/start. The HTML parser.getURLs method is used to retrieve the URLs linked from a given page. Starting with the start URL, we see that it links to two pages, http://example.com/page1 and http://example.com/page2. Following these links, http://example.com/page1 points back to the start page, creating a cycle, while http://example.com/page2 links to http://example.com/page3. Finally, http://example.com/page3 has no outgoing links, ending the crawl. This input helps us understand how we can navigate through a domain and handle cycles effectively while collecting all reachable pages from the starting point. Here, we break down the execution process step by step. First, we initialize an empty visited set, a queue containing just the start URL, and extract the hostname, which is example.com. We begin the crawl by dequeuing the start URL and adding it to visited. Using HTML parser.getURLs, we retrieve its links, both of which belong to the same hostname, so we enqueue them. Next, we process http://example.com/page1, adding it to visited and retrieving its links. One of these links points back to the already visited start URL, so we skip it. Continuing, we handle http://example.com/page2 single quote, adding it to visited and enqueuing http://example.com/page3 single quote, which is its only link. Finally, we process http://example.com/page3 single quote, add it to visited, and find that it has no outgoing links. With the queue empty, we return the list of visited URLs, which now contains all pages reachable from the starting point. In this second example, we explore a scenario where cross-domain links are filtered out. Starting at http://example.com/start single quote, the HTML parser.getURLs method reveals two links, one to http://example.com/page1 and another to http://other.com/page single quote. Since our crawler is restricted to the domain example.com, only the first link is considered valid. http://example.com/page1 is enqueued for processing, while the cross-domain link is ignored entirely. Additionally, http://example.com/page1 has no further outgoing links, so the crawl ends quickly. This demonstrates how filtering by hostname ensures that we stay within the intended domain and avoid unnecessary requests to unrelated domains. Looking at the step-by-step execution for this cross-domain filtering example, we begin by initializing the visited set, the queue with the start URL, and extracting the hostname example.com. The crawler starts with http://example.com/start single quote, adding it to visited. The links retrieved include http://example.com/page1 and http://other.com/page single quote. The latter is ignored since it belongs to a different domain, while the former is enqueued for further processing. Next, the crawler processes http://example.com/page1 single quote, adds it to visited, and retrieves its links, which are empty. With no more pages in the queue, the crawl concludes, and we return the list of visited pages, http://example.com/start and http://example.com/page1 single quote. This highlights how the hostname check prevents unnecessary processing of external links. In the final example, we handle a case where the start page has no outgoing links. Starting with http://example.com/start single quote, the crawler initializes the visited set, a queue containing the start URL, and extracts the hostname example.com. The crawler processes the start URL, adds it to visited, and retrieves its links using HTML parser.getURLs. Since the method returns an empty list, there are no further pages to process. With the queue empty, the crawl is complete, and the result is simply the start URL in a list, http://example.com/start single quote. This case demonstrates how the crawler handles scenarios where the starting page is isolated with no connections to other pages. The time complexity of our solution is influenced by two main factors: the total number of URLs we need to visit and the number of URLs fetched from each page. First, consider the outer loop, which performs a breadth-first search traversal. This loop processes each URL in the queue, and in the worst-case scenario, every unique URL within the same hostname that is reachable from the starting URL must be visited exactly once. Let's define this total number of URLs as n. Consequently, the while loop executes n times. Next, for each visited URL, we retrieve additional URLs using the HTML parser.getURLs method. If a page contains k_i URLs, the sum of these across all pages is denoted as k. In the worst case, where all retrieved URLs are unique and within the same hostname, k is proportional to the total number of reachable URLs. This means the total time spent fetching URLs depends on the sum of all these individual page contributions, giving us a significant part of the time complexity. Now, let's consider the operations related to hostname parsing and membership checks. For every URL retrieved, we parse its hostname using URLparse, next_URL.hostname and perform a membership check to see if it's already visited. Since we use a set for the visited collection, both membership checks and insertions operate in O(1) on average. This means these operations together add up linearly to the total number of URLs processed, which is OK. When we combine all of these considerations, the overall time complexity becomes O(n plus k), where n is the total number of unique URLs visited and k is the total number of URLs retrieved. However, since k is proportional to n, as we only process URLs that belong to the same hostname and are reachable, the time complexity simplifies to O, n. For space complexity, the primary factor is the memory required to store the visited set, the queue, and any intermediate data from parsing URLs or fetching them. Starting with the visited set, it stores up to n unique URLs, and each URL requires O, U, space, where U is the average length of a URL. Therefore, the total space for the visited set is O, n *q. Additionally, the queue used for the BFS traversal contributes to the space complexity. In the worst case, the queue might grow to the maximum number of URLs retrieved from a single page before processing, which would also be proportional to n. Hence, the space complexity of the queue is O, n *q. Furthermore, intermediate data structures like the parsed objects from URL-parse or the temporary lists of URLs retrieved by HTML parser.getURLs require space proportional to the length of the URLs being processed. For any single URL, this intermediate data is O, U, and across all URLs, it sums to O, n *q. However, these intermediate structures are temporary and do not exceed the space required by the visited set or the queue. When we combine all these factors, the overall space complexity comes out to be O, n *q, where n is the number of unique URLs visited and U is the average length of a URL. Comparing this approach to a brute force method highlights the efficiency gains. A naive approach might involve visiting all URLs, including those outside the starting hostname, and manually checking for duplicates. This could dramatically increase the time complexity, especially if the total number of URLs, both valid and invalid, is large. In contrast, our optimized approach restricts the search to URLs within the same hostname, significantly reducing unnecessary work. By employing a breadth-first search, we ensure that all valid URLs are visited in an efficient manner, and the visited set prevents redundant processing. These optimizations not only improve performance but also keep both the time and space complexity manageable. Finally, let's analyze the best, average, and worst-case scenarios. In the best-case scenario, each URL leads to minimal branching, such as when each page contains only one URL. Here, the time complexity simplifies to O, n, where n is the number of pages processed. In the worst case, every page links to numerous other URLs within the same hostname, leading to higher intermediate results and larger memory usage. Even so, the time complexity remains O, n, because each URL is processed exactly once. On average, the time and space complexities are dominated by O, n *q, where U is the average length of a URL. To confirm this mathematically, note that each URL is processed once, and the visited set and queue grow linearly with the number of reachable URLs. Hostname parsing and membership checks, being constant time on average, contribute linearly as well. These factors together validate that both time and space complexities are O, n *q, with n representing the unique URLs visited and U the average URL length. When working on web crawling problems, there are some common pitfalls to watch out for. First, not handling duplicate URLs is a frequent mistake. Without tracking which URLs have already been crawled, your program might revisit the same pages repeatedly, leading to wasted computation and even infinite loops. To avoid this, always maintain a visited set to keep track of processed URLs. Next, failing to respect domain restrictions can lead to invalid crawls. Typically, you're required to limit crawling to URLs within the same domain as the start URL. Ignoring this can violate problem constraints and significantly increase the runtime. Another common issue is improper URL parsing. Relying on simple string operations like starts with or split is risky because URLs can have variations such as subdomains, different protocols, HTTP versus HTTPS, or port numbers. Instead, use a robust URL parsing library to handle these edge cases reliably. Lastly, if you're using multi-threading or multiprocessing, avoid overloading servers with concurrent requests. Too many requests at once can result in HTTP 429 errors, which disrupt the crawling process. Always implement proper throttling to stay within the server's rate limits. Using inefficient data structures is another mistake to avoid. For instance, storing visited URLs in a list instead of a set can drastically slow down your program since list lookups take O, n, time compared to O, 1, for sets. This difference becomes significant when crawling large graphs. Now, let's discuss some interview insights. At its core, web crawling is a graph traversal problem. Think of the web as a graph where each URL is a node, and hyperlinks are edges. Typically, BFS is used to ensure URLs closer to the starting point are processed first, but DFS is also an option, depending on the use case. For large-scale crawls, concurrency can be a powerful tool. Multi-threading or multiprocessing can speed things up, but be cautious about thread safety and ensure you respect server rate limits. For domain validation and URL parsing, libraries like URLparse and Python are your go-to tools. They handle the nuances of URLs far more reliably than manual string manipulation. Lastly, don't forget to prepare for edge cases in interviews, such as malformed URLs, circular references, and pages with no links. The principles of web crawling align closely with several related problems on LeetCode. For example, Problem 133, Clone Graph, involves similar graph traversal techniques and requires careful handling of visited nodes. Problem 200, Number of Islands, is conceptually similar because it requires DFS or BFS to explore connected regions in a grid. Problem 261, Graph Valid Tree, emphasizes connected components and cycle detection, which are relevant when ensuring your traversal doesn't revisit nodes unnecessarily. Finally, Problem 207, Course Schedule, involves exploring a directed graph while accounting for dependencies and cycles, much like managing the constraints in a web crawler. Practicing these problems will deepen your understanding of graph traversal and help you recognize patterns that are common in crawling and related tasks. There are several alternative approaches to consider when implementing a web crawler. First, you can choose between DFS and BFS depending on the structure of the web graph you're crawling. DFS, which uses a stack, is better suited for deeply nested hyperlink structures because it explores one path fully before backtracking. On the other hand, BFS, which uses a queue, is ideal for exploring all links at the current depth first, making it a good choice for tasks that prioritize level order processing. Concurrency is another important consideration. By using multi-threading or asynchronous I/O, you can parallelize requests and significantly speed up the crawling process. However, managing shared data like the visited set requires careful synchronization to prevent race conditions. Finally, while libraries like ScrapePy are great for production-level crawlers, in interviews, you should focus on building the logic manually. This demonstrates your understanding of the underlying algorithms and data structures, which is often more important than using external tools. Great work! We've wrapped up problem number 1236, Web Crawler. We reviewed the problem, discussed strategies like DFS and BFS, and highlighted their applications. Remember, mastering these techniques will serve you well in graph-based problems. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!